Hello APC Mechanics students in Unit 5 Rotation, Class 5, 5.2 Rotational Kinematics. Then Section 1 Variables of Circular Motion. In Unit 2 we have discussed and developed the kinematics for circular motion. The kinematics are dictated by the following variables of motion. So we have the angular position, the angular velocity, the angular acceleration, and the unit of theta is radians, the unit of omega is radians per second, and the unit of alpha is radians per second square. The default positive direction associated with the circular motion is the anti-clockwise direction, while the negative direction would be the clockwise direction, as we have seen previously. These quantities are best understood when introduced in analogy with rectilinear motion. So always remember that theta is in complete analogy with x, omega, which is the angular velocity, is in complete analogy with v, and alpha is in complete analogy with a. This is meter per second square, that would be radians per second, and radians per second square. The set of variables theta, omega, alpha can be related to each other via two different approaches, either via calculus. So by applying the derivative we get omega, by applying the derivative again we get alpha, and we can go backward by applying the antiderivative as well. And the other type is via the type of motion, and by that we mean uniform circular motion in which alpha would be 0, then we're rotating at a constant speed or angular velocity. Or with uniform varied circular motion. By uniform varied, it means that alpha is only constant and not 0. If alpha is 0, which means we're rotating with constant speed, which means the only equation that at our disposal is given by theta is theta 0 plus omega t, which is exactly as x is x0 plus vx multiplied by t. Otherwise, if we're rotating with constant acceleration, we have set of variables which is in analogy with x is x0 plus vx0t plus half at square. The other one would be in analogy with v is vx plus at, vx square plus vx square 0 plus 2a delta x, and the last one, which is delta x, is given by half vx plus vx0 multiplied by t. Now, apart from that, we have seen a connection between linear and circular motion. Now, consider an object M moves along a circle of radius r. So that's the radius of the circle. That is the positive direction. Theta would be the opening angle, and S would be the distance of this arc. In a sense that if you cut the arc like this and you stretch it, you will find that the length of this arc is given by S. So S is the linear distance of the arc. The polar coordinates are given by r and theta. The connections, or the connection, is given by that S is r theta, v is r omega, and a tangential is r multiplied by alpha. So remember that acceleration and alpha are related to each other, given by a is r alpha, but in circular motion we have two types of acceleration, tangential and centripetal. The centripetal is given by v square over r, where the tangential is given by r multiplied by alpha. And AC is v square over r. Consider an object speeding up along a circle. So, first of all, if you need to represent the velocity, it would be always in the direction of motion and tangent to the trajectory. We always have centripetal acceleration whether we're speeding up or slowing down, because we're speeding up, which means our speed increases. And remember that this is due to direction, and that would be due to speeding up or slowing down. Then we would have tangential like that, and the total acceleration would be pointing at this particular point to be down right. Now, if the object is slowing down, the velocity independent whether we're slowing down or speeding up or at constant velocity would be in the direction of motion. The centripetal acceleration would be toward the center, the tangential would be opposite to v, and the acceleration would be pointing like that. Now, what is the difference between v and omega? V is the linear speed of a specified point on a rotating disk. Omega represents how fast is the disk spinning. So now, notice that these two disks, if you consider the point A to be here and the point B to be here, A and B we say are two different points on the gears on the rim, so they have the same linear speed, but what's difference is that they have a different angular velocity omega. So as you can notice from the animation, that the green disk is spinning slower than the red disk. Now here similarly, the smaller disk or the bigger disk is spinning slower than the smaller disk, or we say that the smaller disk is spinning faster than the bigger disk. However, because they are connected by this belt, we say that any point on the rim here, point A and the point B, they have the same linear speed. However, if we consider the same object which is spinning, all points on the disk have the same angular speed, but two different points have different linear speeds. So if you consider a point here A and a point B here, the speed at the point B is greater than the speed at the point A. I will explain why, but all points on the disk, they are spinning the same. So omega B would be equal to omega A. But now notice that the radius of B is greater than the radius of A, which makes omega B RB is greater than omega A RA, and by that VB is greater than VA. So as we go away from the center of the disk, the linear speed would be greater for the same disk, but the omega is the same. Whether if we're talking about two disk system, points, if they are connected points along the rim on each disk, they have the same linear speed, but different omega, as can be seen from these animations. And now for the rest of the video, we're gonna solve some exercises. A disk is free to rotate about an axis perpendicular to the disk through its center of the disk, starts from rest, which means that omega 0 is 0, and accelerates uniformly at the rate of alpha, which is 3 radians per second square for t is equal to 4 seconds. What is the angular displacement? So you can think about delta x being half at square plus vx 0t, and by that we're gonna say that theta, which is theta 0 plus omega 0t plus half alpha t square, we would bring this to the other side, and delta theta starting from rest, that would be 0 plus half alpha, which is 3t, which is 4 square, that would be 16 over 2, which is 8 times 3, that would be 24 radians, and our correct answer for this exercise would be D. A particle moves in the xy plane with coordinates given by a cosine omega t and y is a sine omega t, where a and omega are given. What's the magnitude of the particle acceleration? Speed would be given by a omega. A would be given by a omega square. Now how can we do that? Using calculus. Now Vx would be given by the derivative of this, which is minus omega a sine omega t, minus a omega sine omega t, and ax in this case would be given by minus a omega square cosine omega t. So that's ax. Now Vy would be a omega cosine omega t, and ay would be minus a omega square sine omega t. And if we do the Pythagorean sum for the acceleration, because ax is perpendicular to ay, then a would be the radical of ax square plus ay square. If we do that, that would be the radical of minus a omega square cosine omega t square plus minus a omega square sine omega t square. So that would be the radical of, now that would be, the minus cancels due to the even power, that would be a square omega power 4, or let me say it as follows: a omega square cosine square omega t plus a omega square sine square omega t. You can factor out a omega square to the power of 2. We're left with cosine square omega t plus sine square omega t. So that would be equal to 1. So which is equal to radical a omega square multiplied by 1. So this cancels with that. Then a is 1.5 multiplied by 2 to the power 2. Then 3 times 2, which is 6. meter per second square, which makes E to be the correct answer. A turntable that is initially at rest, then omega 0 is 0, with constant acceleration alpha. We don't have time. What is the angular velocity? Then we're pretty sure we're gonna use omega square is equal to omega square 0 plus 2 alpha delta theta. One complete revolution, each one revolution corresponds for delta theta, which is 2 pi. So that would be 0, then that would be 2 alpha multiplied by 2 pi, which is basically 4 pi alpha. Then omega would be the radical of 4 pi alpha, which makes it C. A windmill, this is a very important exercise, is spinning because of the non-uniform force of the wind. The windmill is originally spinning at a speed omega 0. So the initial speed is omega 0, and the crosswind slows it with an angular acceleration of minus a omega square. Then alpha is given by minus a omega square. What is the angular speed of the windmill at time t is equal to capital T? In order to find the angular speed, we need to find omega. Omega can be related to alpha via two different methods, either via calculus or via the types of motion. Types of motion are restricted to two types. Alpha is constant or alpha is 0. In this case, alpha depends explicitly on omega, which is a variable. So we cannot use the type of motion. We need to use calculus. And we need to set up a differential equation in this case. Alpha is given by d omega over dt. So here what I have done, I have replaced alpha by its differential form given by d omega over dt, because we know that omega is related to alpha by derivative, which means that alpha is equal to d omega by dt. Now here this can be solved by the separation of variables, like the differential equation we used to solve for the drag force. Then we can say d omega divided by omega square is equal to minus a multiplied by dt. Now the minus a can be set on the left hand side or on the right hand side because we're assuming a to be constant. Now we can integrate on both sides. Now what is the integral of omega square dt? This can be done by utilizing it as a power function, 1 over, which is omega minus 2 d omega. Then we increase the power by 1 minus 2 plus 1, and we divide by the total final power. So that would be omega minus 1 over minus 1, which is basically minus 1 over omega. So that would be minus 1 over omega. And here I won't add the constant, I would add it on the right hand side, minus 80 plus a constant. And remember that we're interested in finding omega. Now multiplying the equation by a minus sign, that would be 1 over omega equals 80. Now minus multiplied by a constant is a constant itself. Then in this case, omega is given by 1 over the constant plus 80. Now in order to find the constant, we need to use the initial condition. Initially, the initial speed is given by omega 0. So let me replace t by 0. That would be omega 0 is equal to 1 over the constant plus 0, which means that omega 0 is equal to 1 over c, which means that c equals to 1 over omega 0. Now omega in this case is given by 1 over omega 0 plus 80. Now here what I'm gonna do, so as you can notice that we're approaching the form which is a. Here I would do a common denominator. I would multiply by omega 0 divided by omega 0. And here we would have that omega equals to 1 over 1 plus a t omega 0 divided by omega 0, which is omega 0 divided by 1 plus at omega 0, because the 1 which is in the denominator becomes in the fraction. So double denominator, becomes a numerator. Then omega finally, after this hectic calculation, is given by omega 0 divided by 1 plus at omega 0. And we're interested in the angular speed at t is equal to capital T. Simply instead of t, we'll place a capital T, which makes it a to be the correct answer. Now, a rotating object has an angular position represented by theta a plus bt plus ct square, which is in analogy with theta 0 plus omega 0 t plus half alpha t square, where a, b, and c are constants. A student wants to represent a different rotating object that has twice the angular speed at every moment. What does it mean that at every moment the angular speed is twice? It means that the acceleration is the double. To write the new function, this would only require to double c, because think about it. If c is related to the quadratic term, then c is related to the acceleration, which is angular acceleration. If for each moment the speeds requires to double, so that means that the acceleration should be doubled, because the quantity which represents for the generation of the velocity or the speed is given by the acceleration, only acceleration. Two people A and B are riding a large horizontal rotating platform. The platform rotates around its center. If person A is twice as far from the center as person B, the one who's far from the center would have a linear speed which is greater, but both of them has the same angular speed, so it's either A or C, but person A has greater tangential speed. That means C is correct. A disk initially rotating at 5 radians per second experiences a constant torque for 4 seconds that results in an angular acceleration given by 2 radians per second square. The angular displacement of the disk during those 4 seconds is most nearly, so we have time, then we're pretty sure we need to use delta theta, which is omega 0 t plus half alpha t square, and that would be the initial speed is 5, time is 4, plus half alpha is 2, and the time is 4 to the power 2. Now that would be 20 plus 16, which is 36 radians, making E to be the correct answer. A rotating platform with a radius of 2 meters make one complete turn every 3 seconds. The angular velocity. The angular velocity has a radius has a unit of given by radians per second. Now, one complete revolution, one complete turn every 3 seconds. One complete turns means 2 pi. Therefore, that would be 2 pi divided by 3, which makes it radians per second. Now, plugging that on the calculator, we would have the following value, which is 2.09 radians per second, and the closest to that is given by A. Notice that we have the radius, but we didn't use it. If they're asking for the speed, now that's omega, then the speed in this case would be given by R multiplied by omega. Remember that a trick always in the AP exam, that they give you a redundance given, a given which might not be used. Okay. So based on the dimension analysis unit, radians per second, which means that in the numerator we should have radians, and in the denominator we should have time, which is seconds. A solid disk of mass capital M, radius capital R, and rotational inertia I is free to rotate about a fixed frictionless axis that is perpendicular to the disk through its center as shown above. A force of constant direction and constant magnitude capital F is exerted on the disk if the disk is moving clockwise with an angular speed of 5 radians per second. Then the initial angular speed is given by 5 radians per second. With angular acceleration of magnitude alpha is 1.3 radians per second square. Notice that both they are considered in the clockwise direction. What is the angular speed omega after 3 seconds? We're gonna use alpha t plus omega 0, which is 1.3 multiplied by 3 plus 5. Now plugging that on the calculator, we would have a value given by 8.9 radians per second, making D to be the correct answer. A fan blade rotates with angular velocity omega, the angular acceleration. Now we know that alpha can be computed from omega using calculus. We cannot use the type of motion because that is not linear. Then the constant would be 0. That would be minus 4.4 multiplied by t. Now alpha for t is equal to 3 seconds. That would be what? Minus 4.4 multiplied by 3. Plugging that on the calculator, we would have a value given by, which is given by minus 13.2 radians per second square, making C to be the correct answer. A disk with a diameter of 40 centimeters, D is 40 centimeters, which is 0.4 meters. Then the radius in this case is given by D divided by 2, which is 0.4 over 2, which is 0.2 meters. So remember a trick in the AP exam that they always play with the distances. We might use it and we might not. Let's check. In part A, derive an expression for the angular acceleration. Can be computed from theta using derivatives or using calculus because t power 4 is undefined as type of motion. Then omega in this case would be given by 3t minus 8, and alpha would be given by, so cube, sorry, that's wrong, that would be t cube minus 8. Then alpha would be 3t square, and if we need to calculate the linear speed, so that for part A, alpha is given by 3t square. So let me write, okay. Now in part B, we need to find the linear speed. V equals to r omega at the point on the outside edge of the disk at t is equal to 4 seconds. The radius is given by 0.2, and omega would be given by t cube, but we need to replace t by 4, so that would be 4 to the power 3 minus 8. Alright, plugging that on the calculator, we would get a value of 11.2 meters per second. Now a flywheel with a diameter 3.5 centimeters, then directly let's determine the radius. So that would be d, which is 0.035 meters. Then the radius would be 0.035 divided by 2, which is basically 0.0175 meters, and rotating at 2500 revolutions per minute. So remember that each one revolution corresponds to 2 pi, and 2 pi is being expressed in radians, okay? Comes to a halt. Halt means stop in 1.5 seconds. In part A, we need to calculate the magnitude of the tangential acceleration. A tangential is r multiplied by alpha. We have the value of r, so we need to determine first alpha. Alpha can be determined by referring to the type of motion. So here there is something missing in the given. They should say that the tangential acceleration assumed to be constant in order to refer to the type of motion. Now, in order to calculate alpha, we can do the following trick. We can say that omega equals alpha t plus omega 0. Because it becomes to a stop, then the final omega would be 0. 0 equals to alpha t, now t, which is 1.5. Now it's left to determine what is omega 0, and it's already given, which is 2500 revolutions per minute, but we need to express it in radians per second, and this can be done by the following. So omega 0 is 2500 revolution per minute, which is 2500 times 2 pi, because each revolution is 2 pi, divided by minute, which is 60 seconds. Plugging that on the calculator, we would have a value of almost 261.8 radians per second. Then the initial angular speed is given by 261.8. So 0 would be equal to alpha multiplied by 1.5 plus 261.8. Then in this case, alpha is given by minus 261.8 divided by 1.5, and alpha eventually, which is the angular acceleration, is given by minus 174.5 radians per second square. But that's not enough because we want the tangential acceleration. So let me do it here. A tangential would be given by r multiplied by alpha. R is given by 0.0175 and minus 174.5. Plugging that on the calculator, we would have a value of almost minus 3.06 meter per second square. And remember that both angular acceleration and acceleration, they are vector quantities, so we expect that they might be positive or they might be negative. So let me write down that alpha was given by minus 174.5 radians per second square. Now in part B, so let me just also again write that the initial angular speed is given by 261.8 radians per second. Now based on that, we can determine how many revolutions the flywheel makes as it stops, because delta theta, which is omega 0 t plus half alpha t squared, now that would be omega 0 is 261.8 multiplied by 1.5 plus half multiplied by alpha, which is minus 174.5 into 1.5 square. Plugging that on the calculator, we're gonna get 196.4 radians. But we know that each one revolution, we need the number of revolutions corresponds to 2 pi in radians. Now what about 196.4 radians? That corresponds to how many revolution? Then simply we do 196.4 divided by 2 pi. Plugging that on the calculator, we would have a value of 31.25 revolutions. Now moving on to the next exercise. A DVD rotates from rest and the initial angular speed is 0 to 1500 revolutions per minute. So we can determine the final angular speed in radians per second by multiplying by 2 pi, because each revolution corresponds to 2 pi, and dividing by 60. Plugging that on the calculator, the final speed is 50 pi radians per second. In part A, we need to find the uniform angular acceleration, which means that we can refer to the type of motion. Omega is alpha t plus omega 0. From rest, that would be 0. Then alpha would be omega, which is 50 pi, divided by 4, and that would be 12.5 pi radians per second. That's it for part B. For part A. In part B, how many revolutions, which means delta theta, which is omega 0 t plus half alpha t squared, that's 0, which is half 12.5 pi multiplied by 4 to the power of 2. Plugging that on the calculator, that would be 100 pi in radians. But remember that we need to determine the number of revolutions. If each one revolution corresponds to 2 pi, then what about 100 pi? They corresponds to how many revolutions? So we simply just cross multiply. Then 100 pi divided by 2 pi, that would be 50 revolutions. Now how far, which means the distance traveled, which is the length arc, which is S is equal to R theta. The radius is given by 5 centimeters, which is 0.05, multiplied by theta, which is 100 pi. So that would be 5 pi, and the unit would be meters, because S is in meters. And finally, the last exercise as an exit ticket. We have omega. We need to derive an expression for the angular acceleration, and this is done by calculus, which is minus 1.4 t. We drop down the power, quadratic becomes linear. B, what is the instantaneous angular acceleration at 2 seconds? So we replace time by 2. That would be minus 1.4 multiplied by 2, and that would be minus 2.8 radians per second square. If they would to ask us about the magnitude of the angular acceleration, we would say 2.8, because also a common trick in the AP exam to ask us between the vector quantity itself or the scalar. Then that's it for me in this video, guys. See you soon in a new one.